Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be turning our attention to AS Physics for CAIE, and in particular, we're going to be doing a crash course on the topic of particle physics. Now, particle physics is the last topic in AS Physics, and it's the first introduction to modern physics, so it will be fairly new for many of you. Again, this is only a crash course, and this is a topic that requires quite significant reading and studying from your textbooks and from other resources that you may have, but it's a fairly significant one. And so the first part of this topic is that we understand the atom, and we're going to just assume a very basic model of the atom, just to make it easier for visualization purposes. But I'm going to assume that the atom is this circular thing. It's not completely true, but if my atom is the building block of all of the matter that I have in the universe, well, naturally I'm curious and I want to zoom into this atom. And if I assume a model such as the Bohr model, I can get that this atom actually has a nucleus at its core, a tightly packed nucleus at its core, and surrounding this nucleus, we have electrons. So I'm going to draw the electrons in red, and I'm going to draw them really small because we know the electrons are tiny compared to the things in the nucleus. And these electrons are orbiting, quote unquote, orbiting the nucleus. Now these electrons, they are small particles, they are fundamental particles. We'll explain what that means later. And these electrons have a charge of -1, a relative charge of -1. And we'll give these values an actual physical meaning soon, but we'll assume that for now it's one elementary unit and it's negative. Then inside the nucleus, we have protons and neutrons. And neutrons are particles that are relatively heavy, much heavier than electrons, that's for sure. And neutrons, well, you can see from the word from the first part of the word, they are neutral. They have no charge. So neutrons don't have any charge. And the last things left in the atom is the proton. And guess what? The protons do have a charge. And the charge is equal in magnitude to the charge of the electron, but opposite in sign. So the charge is +1e, where E we'll define now is simply the elementary charge, 1.6 times 10 to the minus 19 coulombs. Every charged object must have an integer multiple of this charge, 1.6 times 10 to the minus 19 coulombs. Tiny amount of charge. It's the same for the proton as it is for the electron, and it is positive for the proton but negative for the electron. Remember, negative and positive charges will attract each other, and positive charges will repel. So essentially, there must be something happening in the nucleus to keep these protons together because they would like to repel each other. But we're going to talk about that later on. The thing that's holding them together in the nucleus is called the strong force. Now, before we go any further, we need to define what an atomic mass unit is. We simply can't work in kilograms anymore because we can see that these particles are tiny. One atomic mass unit is roughly the mass of a proton and neutron. A proton and neutron would ideally have the same mass outside the nucleus, but due to some strange effects happening inside the nucleus, their masses are slightly different. And the atomic mass unit is 1.66 times 10 to the minus 27 kg. Why do we use this? Well, purely we use this because this is convenient. We'd rather use an atomic mass unit than use something times 10 to the minus 27 kilograms every time. Makes a lot more sense at least. So what we can then define is, let's tabulate our particles in terms of their mass and charge. And so we have the proton and neutron, which exist inside the nucleus. Both have roughly the same mass, relatively heavy. The electron is a particle that's extremely light. So light that it's easy to move. Hence, it is generally what we use as charge carriers. So firstly, we'll tabulate. We'll have a column for the mass of each of these particles in atomic mass units U, and the charge in terms of one elementary unit. So 1e, remember, is 1.6 times 10 to the minus 19 coulombs. The mass of a proton is almost identical to the atomic mass unit, is 1.0073. And the charge is plus 1e. For the neutron, the mass is almost very similar. It's close to 1 atomic mass unit, but it's slightly different. Inside the nucleus, it's 1.0087 atomic mass units, and it has no charge. And the electron is much tinier. It has a mass of 0.00055 atomic mass units and a charge of minus e. Remember that the electron and proton do not have the same masses. Do not get these confused. The mass of the electron in kg is on the order of 10 to the minus 31 kg. So it's much smaller than the proton and neutron. Now, in general, atoms are uncharged. So a typical atom shouldn't have a total charge on it. Well, if we look at what we've described above, this means that specifically the number of protons in an atom should equal the number of electrons. And so this means that the total charge will balance, as I have as many positive charges as I do negative charges. And so this is an uncharged atom. But there are cases where an atom can have a net charge. And that happens when it loses electrons or gains electrons. So if I have an uncharged atom, this uncharged atom can gain a charge, and a charged atom is what we call an ion. So it can become a positive ion if it loses negative charge. If it's become less negative, that is more positive. So if it loses an electron, it becomes a positive ion. Why do I say it loses an electron? Well, firstly, electrons are very far out from the center of the nucleus. If we look at the diagram of the atom, there's a big distance from the nucleus to the electron. Electrons are far from the nucleus and especially electrons in the outer orbits around the nucleus, they're loosely bound to the atoms and are easy to get rid of. Also very light, and so they don't require much energy to move. On the other hand, an atom can gain an electron. So an atom can become more negative by accepting an extra electron, and this becomes a negative ion. So here, the neutral atom gains an electron, hence gains a negative charge and becomes a negative ion. So a negative ion has an excess of electrons, a positive ion has fewer electrons. So let's take an example. Let's look at the example of lithium, let's say. So I have my imaginary orbit. Again, this is imaginary. In reality, electrons don't do this circular orbit as I'm showing here. But we'll imagine for now that the electron, at least this analogy kind of works fairly well for now. So I'm going to draw my 3 protons, and I'm going to draw 3 neutrons, but as you can see, I only have 2 electrons. So this is called the lithium ion, and because of chemistry we won't discuss, this is a positive ion. It prefers to be a positive ion. It prefers to give away one of its electrons. And so what I'm left with is 3 protons and 2 electrons. So we can see there's an imbalance of charged particles in this atom. And if I were to calculate the total charge, then this charge would be plus 3e for the 3 electrons minus 2e for the 3 protons rather, and minus 2e for the 2 electrons, so I have a total charge of plus 1e. And hence the lithium ion can be represented by the symbol for lithium Li with a little plus sign as a superscript. Which brings me on to the next point, which is how we can represent atoms. So we want to find a way that we can write the atomic structures without too much of effort. Instead of writing the name for every element out, how can we represent atoms? Well, firstly, let's define symbols like we usually do for physics. We call the number of protons in the atom the proton number or the atomic number. These are just terms that we use. The proton number makes sense, atomic number is a little bit more abstract, but we give it the symbol Z, an uppercase Z. We then define another quantity called the nucleon number, also known as to chemists as the mass number of a particular element, that is for a particular substance. And this is the number of neutrons and protons. So we call it the nucleon number because the things inside the nucleus are called nucleons. So basically, a neutron is a nucleon and a proton is a nucleon. And this total number of neutrons plus protons, we give it the symbol A. So remember, this nucleon can be either a proton or a neutron. So how do we represent an atom? Well, we represent it with a symbol for the atom. For example, lithium was L, an uppercase L and a lowercase I. And then to the left, we use the subscript Z at the bottom for the atomic number and the superscript A at the top for the mass number. So we have symbol of element in big, in bold, and then we have the mass number on the left and above, and the atomic number on the left and below. So this is sort of the convention, at least that we'll use for AS physics. So an example of this would be carbon-12. So let's take the carbon-12 atom. Carbon-12 can be written as carbon-12-6. And what we can see here is that the number at the bottom, the atomic number, which again is the number of protons, is 6. So carbon-12 has 6 protons and 12 nucleons. So that gives me the number of nucleons, but doesn't really tell me the number of neutrons. So therefore, the number of neutrons will be what's remaining in the nucleus. 12 nucleons, which is protons and neutrons, minus 6 protons, and I'm left with 6 neutrons. And so this atom has as many protons as it has neutrons. Is it always the case that the number of protons and neutrons will be the same? Well, no. These atoms that have different numbers of protons and neutrons are called isotopes. And isotopes of the same atom will have the same number of protons. So all isotopes have the same number of protons, but varying numbers of neutrons. And so an isotope is defined as any element that has the same number of protons, but varying numbers of neutrons. So let's look at an example of what an isotope could be. So we could go back to the previous example that we use of carbon-12. So think carbon-12, 6. And this has 6 protons, as we said, and we can see that this has 6 neutrons as well. There's another isotope of carbon, which we use sometimes for carbon dating, radioactive dating, carbon-13. Carbon-13 has also 6 protons. The number on the bottom is still a 6. But now 13 minus 6 gives me 7. So what's remaining must be 7 neutrons. And so we say carbon-13 is an isotope of carbon, or carbon-12 is an isotope of carbon, because there are many different types of carbon. We can also get carbon-14 with 6 protons and 8 neutrons, and so on. And this could be the case for many different types of atoms, not just carbon. So that's what an isotope is. So the number of protons and neutrons need not be equal. The next part of the topic was on radiation. Now, we cover radiation again later on in A-level physics, but to begin with, what is radiation? We all have an idea, an understanding that radiation is something that's unsafe, something that is harmful. But do we really know what it is? Now, there are 3 types of radiation: alpha particles, beta particles, and gamma radiation. Basically, when an atom is unstable, remember, everything in the universe wants to tend towards stability. When an atom is unstable, it can randomly and spontaneously give off any one of these types of radiation in order to regain stability, or at least be more stable than it was before emitting any of these particles. Most times when radioactivity occurs, when an unstable atom gives off one of these particles, it'll give off more than just one and continue to emit a radioactive particle until it becomes the stablest it can. And that's when the atom is no longer radioactive. So the 3 types of radiation are alpha particles, beta particles, and gamma radiation. Again, something you've probably heard before, but never really had the chance of understanding. So let's describe first an alpha particle. Simply put, an alpha particle is a helium nucleus. It is the nucleus of a helium atom. So it's the helium atom minus the electrons. Essentially, it would be written as He, the symbol for helium, 2 protons, 2 neutrons, so the proton number is 2 and the mass number is 4. From here we can see that the mass would be 4 atomic mass units, because there's 4 things in this nucleus. And the charge would be 2e. Doesn't have any electrons, it only has 2 protons, so it will be a plus 2e. And you can read further, but what you will find is alpha particles are highly ionizing. They are extremely dangerous, even though they don't penetrate that far. In fact, the danger lies in the fact that they can't penetrate that far, because that means if they were to pass into your body, they would most likely be absorbed by the atoms of your body. And they are highly dangerous. How does alpha decay occur? Well, basically, let's take an example. Take an unstable atom, uranium-234, where the proton number is 92. This can randomly and spontaneously, basically at any point in time which we can't predict, decay into another atom that's slightly more stable, not completely stable, but slightly more stable, and in the process give off this alpha particle and also give off some energy. So in this process, we have uranium-234 becoming thorium-230 plus the helium nucleus 42 or 24, which is the alpha particle, plus some energy. Okay, and the uranium nucleus here is called the parent nuclide. It is the initial unstable atom. The daughter nuclide is the atom that is formed. This is just some terminology. And then we have the alpha particle being released. We can sometimes just represent this with the letter alpha, the Greek letter alpha, or just helium 4, 2, and then some energy. That energy is usually given to the alpha particle. Now, what happens here is in these alpha decay processes, all the alpha particles that are produced have the same energy. So they have the same kinetic energy, provided the parent nuclide is the same. So if uranium-234 is constantly decaying, the helium particles that are produced will always have the same kinetic energy. Now, another thing we have to make sure is that things are conserved. In physics, we have a lot of conservation laws. So let's look at the number of protons and neutrons on the left-hand side and make sure they balance to the right-hand side. Again, we can't have protons and neutrons simply vanishing. So on the left-hand side, we have uranium-234, and we have an atomic number of 92. So Z is 92, and the mass number A is 234. Let's check if this balances what we have on the right-hand side. On the right-hand side, we have the atomic number Z equal to 90 for the thorium, plus 2 for the alpha particle, which is 92. And the mass number A, 230 for thorium, plus 4 for the alpha particle, which is 234. So we can see that the atomic numbers and mass numbers are all conserved. So this reaction can actually happen. And the only extra bit of information we have is that some energy is released, and that energy is usually given to the alpha particle to be fired off at a high speeds, and some of the energy goes to the thorium atom as it recoils. Most of the energy will be observed with the alpha particle that actually moves off with a great amount of speed. The next type of radiation we have are beta particles. We'll go through the same process that we did for the alpha. Now, beta particles are not helium nuclei. They're actually extremely fast-moving electrons. So you're probably wondering, well, what's so harmful with an electron? Well, the fact is that they are moving very fast, and that's what makes them quite harmful. So beta particles could be fast-moving electrons. They could also be the antiparticles of electrons. We'll talk more about antiparticles later on, but basically an antiparticle of any matter particle is or has the same mass but the opposite charge. So this beta particle here has the same mass, the positron rather, has the same mass but the opposite charge. And all antiparticles have the same mass as their particle, well, counterparts, but their charges are opposite. We can also call the positron an anti-electron. So it has the same mass, so irrespective of whether we have a fast-moving electron or a fast-moving positron, the mass is 0.00055 atomic mass units, which we defined earlier. So you can see that it's a fairly tiny particle, but the energy, the danger arises from the fact that it's moving at a very high speed, sometimes 99% the speed of light. So the actual decay that leads to the formation of these particles, there's actually two types. There's beta minus decay, which we'll talk about first. And one example of beta minus decay is carbon-14. So we spoke about carbon-14 earlier, an isotope of carbon. Carbon-14 can randomly and spontaneously decay to form nitrogen-14 plus a beta minus particle or an electron. We'll give it the symbol 0 minus 1 so that we can conserve charge. symbol E, and mass number is 0. Obviously, there aren't any protons or neutrons in an electron, and atomic number -1. So that's the total charge, which is -1. If it were a proton, it'd have a charge +1. And another particle is formed, which we aren't going to talk about in too much detail, but it's called an electron antineutrino, or we're just going to call it an antineutrino because that's what it is. It's a very light particle, can move very fast, hard to detect as well, an antineutrino. And there's some energy in this process as well. So this process is slightly different from the process of alpha decay, because here we have beta particles produced, but they don't all have the same energy as the alpha particles did, but they have different energies. And the reason why they have different energies, you probably guessed it, is because they share the energy that is released by this decay with the neutrinos. And that symbol that I wrote looks like a V, but it's actually the Greek letter nu. And N for nu, N for neutrino. And again, we have a parent nuclide, a daughter nuclide, a beta minus particle, which we can also represent with the beta and a little -1, and an antineutrino. So let's do the same conservation exercise that we did before. If you look at the left-hand side, the atomic number Z is equal to 6, and the mass number A is equal to 14. On the right-hand side, we have the atomic number Z being 7 for nitrogen, and cleverly we label that of the electron as -1. This is so that charge can be conserved. And there's nothing for the neutrino, so that's equal to 6. Similarly, the mass number, again, neutrinos are so small, even antineutrinos are so small that they have no mass, or no significant mass. So the mass number is simply 14. And so yes, this decay can happen energetically because we have these numbers balancing. Now what's actually happening is a very special type of transformation is happening. We'll probably discuss this later on as to how it's happening. But the weirdness of particle physics is that a neutron actually decays into a proton, an electron, and an antineutrino. So if you look at the equation above, carbon-14 has 6 protons, but nitrogen has 7. The number of nucleons is the same, so carbon has 6 neutrons and nitrogen has 7. And so a proton is becoming a neutron in a neutron in the carbon is becoming a proton in the nitrogen, an electron and an antineutrino, and a little bit of energy. So that's the actual transformation that happens on a very small scale. It's confusing, but this is the way particle physics works. So the other type of beta decay is beta plus decay. And you guessed it, that means a positron must be released. So one example of this is carbon-10. So carbon-10,6 can randomly and spontaneously decay and become boron-10,5, one less proton and one more neutron, plus a positron. We'll write this as E plus 1, 0, and this time instead of an antineutrino, a neutrino is released. Atomic number 0, mass number 0, and then again some energy which can be shared between the neutrino and the positron. And again we have a parent, a daughter, a beta plus particle, and then this is not an antineutrino but a tiny particle called a neutrino, which we aren't really going to focus on. And you can see the transformation here is that a proton decays into a neutron, a positron, and a neutrino. Very similar to the transformation above, with the proton and neutron switching places, electron replaced by a positron, and the antineutrino replaced with a neutrino. So yes, particle physics is weird that way, but we have to understand the oddities as it is a complicated topic, especially at advanced levels. So on the left-hand side, if we do conservation exercise again, we see carbon has an atomic number of 6 and a mass number of 10. On the right-hand side, we have the atomic number Z is 5 for the boron plus 1 for the positron, and this equals to 6, with the mass number A equal to simply 10 for the boron. And so the atomic numbers and mass numbers balance again, and so everyone is happy. And like I said, in this case, the transformation is similar, but in this case, a proton, we write a proton as atomic number 1, nucleon number 1, kind of makes sense. 1 proton, 1 nucleon. The neutron has obviously 0 protons, but 1 neutron, plus a positron, 1, 0, a neutrino, and some energy. So this is the transformation that happens inside an atom when beta plus decay occurs. Quite a weird interaction for a proton to suddenly become a neutron. But again, we'll maybe try and explain this a little later on if we're brave enough. And the last type of radiation that's released is actually what we define as radiation, gamma radiation. And gamma radiation is actually electromagnetic waves. So a gamma particle, or gamma ray as we call it, is an electromagnetic wave, just like your radio waves, microwaves, visible light, X-rays, etc. But it has a very high energy and a very short wavelength. Remember, short wavelengths correspond to high energies. So the wavelength is about 10 to the minus 11 to about 10 to the minus 13 meters. And since it is an electromagnetic wave, as you know from the spectrum, will have no charge. So just because it's an electromagnetic wave doesn't mean that it's not dangerous. It is highly dangerous. Will usually pass through a good few centimeters, maybe a few meters of material, but still carries huge amounts of energy. So gamma decay is a little different because there obviously isn't going to be change in atomic and mass numbers. So an example of gamma decay is thorium-234-90, which we met earlier on. So like we said, thorium is a little bit more stable than uranium-234, but still not ideally completely stable. And we put a little star to represent that it's unstable, it's excited, as we say. And this thorium can remain as thorium-234, weirdly enough, but give off a gamma ray in the process. So the star tells us that our parent nuclide in this case, is excited, and our daughter nuclide, which is exactly the same atom, now actually has less energy. So we can say this is de-excited, meaning it's in a state that has less energy. It's you before and after having, or rather after having coffee, and then a long time after having coffee, going from excited to de-excited in some amount of time. And the emission is gamma ray, so the emission is energy. And this gamma ray has, like we say, a very short wavelength. So these are the three types of radiation, how they occur, some examples. Would be wise to study more of these examples. But what this leads us on to is a very important experiment carried out by Rutherford. And I think for you, it is described as the alpha particle scattering experiment. Now, it's probably one of the first times in AS Physics that you are actually asked to understand and know and memorize the observations from an experiment and then discuss their importance. So the alpha particle scattering experiment, also called Rutherford's experiment, was carried out by Rutherford, I think also by Geiger and Marsden, if I'm not mistaken. But basically, in this experiment, and you can read up on the experiment, how it was carried out, etc., alpha particles, which we said were helium nuclei, were fired at a thin gold foil. And Rutherford sort of had an idea of what he wanted an idea rather of what the atom looked like. And so he decided, well, if I fire alpha particles towards gold foil, I should be able to get a picture of what the nucleus looks like. And what he found was that most alpha particles, as they passed through the gold foil, to his surprise, were undeflected. I think he may have had an idea of maybe a rough idea of what the atom looked like, but this experiment sort of helped him solidify those assumptions. A few of the alpha particles, very few alpha particles, were deviated, and they were deviated by specifically small angles, so roughly 10 degrees or so. So some went through undeflected, many went through undeflected rather, few alpha particles were deviated by small angles, and a very tiny fraction, whatever was remaining, actually deflected greater than 90%. So they had a deflection on them of the direction of motion that was greater than 90 degrees. And so a tiny fraction of the alpha particles deflected greater than 90 degrees. So Rutherford had to make a conclusion based on this experiment. And yes, you need to know these conclusions as well. So why was this significant? Well, we could now actually tell with some sort of certainty that atoms are mostly empty space. If most of your particles are going through and deflected, I can see a physical, complete gold foil, but my atoms, my alpha particles, are not being disturbed by the atoms of the gold. Something strange must be happening. And that strangeness happened because the atoms are mostly empty space. There was no deflection when the alpha particles were moving through because they were moving empty space through empty space, technically. The fact that a few particles were deviated by small angles means that the core, the nucleus of the atoms of gold and of the alpha particle, generally small and compact. So the core is dense and small. It's only when the alpha particles got really close to the nucleus of the gold that they were actually moved. And so there'd have to be a tinier percentage of them being deviated by the nucleus of the gold. And the very fact that they were deviated shows that they had to be charged. The nucleus must have a net charge. Now we know that charge must be positive, since the electrons lie outside the nucleus and don't affect the charge of the nucleus. So the nucleus of the gold atoms must be charged in order for them to deflect the positively charged alpha particles. So these were the observations that Rutherford made in the alpha particle scattering experiment and the conclusions that he made from each of those observations. So again, like I say, it's probably the first time that you have seen a time where you have to explain an experiment, but the experiment is a significant one. It's an important one. It has helped our idea of the atom, helped us build a picture of the atom many years ago. So now, going away from radiation, we need to talk about what types of particles, because I use the word particle kind of freely, And the idea of a particle will change in A-level physics, but you need not stress about that, at least for now. What are fundamental particles? So here's my little electron. This electron, if I look at it, actually, I cannot break this electron any further. I cannot break it down any further. I cannot subdivide it. And so this electron is what we call a fundamental particle. Its antiparticle, the positron, is also a fundamental particle. It can't be broken down any further. But strangely enough, what we've found, and we've even found experimentally from smashing these nucleons together, is that particles like protons and neutrons, believe it or not, are not fundamental. I can break open these protons and neutrons, smash them together, well, specifically protons. If I smash them together really fast, I can tell that there's something inside them, actually many things inside them. And so they are not fundamental particles. So let's zoom in a bit more. Let's assume my proton, making a lot of circular assumptions here. Again, this is just me trying to depict something that really doesn't have a picture. But inside let's take a proton, for example. Inside a proton, there are 3 smaller particles, and we call these particles quarks. And so this entire picture represents a proton. But inside the proton, there are 3 quarks. This is specifically for the proton now, but there are 3 quarks, 3 tinier particles, even tinier than the proton itself. And then they are held together by something called the nuclear strong force. And the strong force is responsible. It's a very weird force. It only happens at small distances, and it only happens between quarks. And the strong force is what's responsible for holding the quarks together in the nucleus, but actually more for holding the protons together inside the nucleus. And so we can define these particles and classify these particles depending on the effects that they have. So you may have heard this word before, but these things that have, quarks in them, these things that are affected by the strong force, are called hadrons. And so any particle that is affected by the strong force is called a hadron. And this includes your protons, neutrons, etc. Any particles that are not affected by the strong force are called leptons. And this includes your neutrinos and your electrons, etc. So it's a weird force. At least classically, at least on the surface, we can think of it as any other kind of force, like a gravitational force or an electrostatic force, etc. But it is a lot more complicated than that. We won't go into too much detail talking about how it works, but just remember the reason why protons can stay together inside a nucleus and they don't repel each other is that because at very small distances, as the protons are in an atom, in the core of an atom, the strong force overcomes the electrostatic force. And remember, the electrostatic force is actually quite strong. So the strong force, hence, is given the name strong, right? And hadrons can be broken down even further to baryons. Baryon is any hadron, any particle affected by the strong force that is made up of 3 quarks or made up of 3 antiquarks. An antiquark is just like a quark, but it's a particle with, the opposite charge. If it isn't a baryon, then it's a meson. And mesons are slightly different. Mesons compose of 1 quark and 1 antiquark. So we can see that protons and neutrons are baryons. Now, the thing that distinguishes quarks from one another is what we call a flavor. Not the flavor in terms of what you're thinking, in terms of food, but it's simply a way of defining or differentiating between quarks because we have so many of them. So we call the quark flavor, or we label the quark flavor, just way of describing different types of quarks. And there are many properties that will identify quarks, but we're just going to talk about the charge for now and ignore things like the strangeness and so on. So what we found, although in batches, we now have that there are 6 quark flavors, and they are up, down, strange, charm, bottom, and top. So there are 6 different types of quarks. We can put these arrangements of quarks together, hold them together with a strong force, and create a baryon or a meson. And each of them have their own symbols. Up is U, down is D, strange is S, charm is C, you guessed it, bottom is B, and top is T. And each of them has a specific type of charge. So weirdly enough, we actually attribute the total charge of the proton or the neutron to the quarks, which have sort of a subdivision of charge. Now don't be too afraid. These charges these quarks don't really exist freely. They'll only exist inside the baryon or meson, inside the hadron, but they don't last or don't live for a very long time when they're outside of the hadron. And so the charges are as follows: plus 2/3 E for the up quark, minus 1/3 E for the down quark, minus 1/3 E for the strange quark, plus 2/3 E for the charm quark, minus 1/3 E for the bottom quark, and plus 2/3 E for the top quark. Again, you'll find these charges in your textbook. And really, there isn't a special way to memorize them. It's just, well, you need to. And so if I put these charges together, what I will get is they will eventually have to add up to plus E or minus E, or some multiple, some negative or positive integer multiple of E, because as we know, charges must be a multiple of E. So they don't technically have these charges, but we sort of attribute a portion of the hadron's charge to these quarks. And so let's do an example. Let's use the example of a proton. Now, a proton's total charge is positive 1e. It turns out that a proton, if we break it open, we see that it's made from 2 up quarks and 1 down quark. That's a plus 2/3 E charge, plus another 2/3 E charge, and you guessed it, the down quark has a charge of minus 1/3 E, so the total charge is definitely E. Now, this will not work for a neutron, obviously, because a neutron is neutrally charged. So the charge on the neutron is 0, and we found that the neutron is made from an up quark, a down quark, and another down quark. So this is a charge of plus 2/3 E, minus 1/3 E, minus another 1/3 E, and yes, the total charge on the neutron is 0. So weirdly enough, our hadrons all comprise of these little tiny particles that are quarks. If you wanted the charge of an anti-quark, the anti-up quark, for example, would have a charge of minus 2/3. The anti-down quark would have a charge of plus 1/3. So an anti-proton would have an anti-up, another anti-up, and an anti-down. And this would give it a charge of minus E. And so it would have the antiparticle for each one of the quarks, and hence we would be minus 2/3, minus 2/3, plus 1/3, which would be minus 1. And so an antiproton would have the same mass, but opposite charge. And so these are the fundamental particles. And we can actually use this description to explain beta decay. So this description of quarks can be used to explain how beta decay occurs. So let's look at beta minus decay. So for beta minus decay, we said a neutron N01 becomes a proton 11. We have to conserve the numbers on both sides, so that's plus an electron, plus a beta particle, a negative beta particle, plus an antineutrino. For antiparticles, we use a line on top of the symbol for the particle, as I did for the up and down quarks, just a horizontal line above the symbol for the particle. So what we know is that a neutron has 3 quarks, that is up, down, down. And on the right-hand side here, the only place I will find quarks is in the proton. And I also have 3 quarks, up, up, and down. And so if I look at this interaction, what I find is that the lepton number, if I were to count the number of leptons on either side, that the lepton number on either side is conserved. How do I know that? The lepton number of the electron, of any particle that's a lepton, is 1. So an electron is a particle. The lepton number of anything that's a lepton but an antiparticle, like the antineutrino, we give it, by definition, a lepton number of -1. So any particle that's a lepton has a lepton number of 1. Any antiparticle that's a lepton has a lepton number of -1. And on the left-hand side, the lepton number of the neutron, well, it is a neutron. It is not a lepton. It's a hadron, and so it doesn't have a lepton number, 0. And so what I find is that the lepton number on the right-hand side is equal to the lepton number on the left-hand side. +1 and -1 gives me a total lepton number of 0, and the lepton number of the neutron is also 0. So lepton number is conserved. However, what I have is a down quark on the left-hand side becomes an up quark on the right-hand side. And what this means is that the flavor is not conserved, because now I have more down quarks on the left-hand side than I do on the right-hand side. So even though lepton numbers are conserved, the quark flavors are not conserved. So why am I telling you all of this? Because this simple example tells us that this interaction of beta minus decay doesn't happen due to the strong force. So the strong force is not responsible for beta minus decay. Beta minus decay is actually understood, but not that well understood. And it is due to another type of force called the weak force, which you would probably learn more about if you study physics any further. So when the flavor is not conserved, the interaction is not due to the strong force, but actually due to the weak nuclear force. So that's been a crash course on the topic of particle physics. There's a lot to remember, a lot to understand, and a lot to work on, and does require you to understand things that you probably haven't seen before. But at the same time, it's very interesting, and it leads on to topics in A-level physics that are very important. So it's good to get a solid foundational understanding now, as it will help unbelievably in A-level physics. Please drop a like, subscribe, drop a comment in the comment section below. Let me know if these videos are helping, and I will see you again on the next crash course. Until then, I'm Mr. K, and we'll see you again next time on Everything is Relative.